I'm Mark Abel. I'm the Associate Director of the Institute for Energy Efficiency, and I wanted to welcome you to the 2021 Institute for Energy Efficiency Seminar Series. And I'll be your moderator today. I want to tell you this is the first of a great lineup of talks we have coming in this time slot. Mahdi will be speaking today, and we'll introduce him in a moment. And you have a great treat in store for you with Mahdi's talk. A couple of weeks from today, we have Josh Smith, professor and inventor from the University of Washington, talking about perpetual computing. And there will be talks approximately every couple of weeks after that for the term, for the next couple terms, including folks like Eric Mazanet, eminent professor here at UW, talking about data center energy efficiency modeling. We have some really wonderful stuff coming up as well. A few instructions for today. We are asking that you please keep yourself muted unless you're asking a question. If the current size of the group stays about this or a little bit bigger, we'll do questions as we go. And in that case, the easiest thing is probably you can try to unmute yourself, but you also, it would be great if you could use the chat feature. We'll keep an eye on that if you really want to jump in on something. We'd like to keep it interactive if we can, but we also don't want to get out of control. So we'll go with that, Mahdi. So I wanted to introduce Mahdi and tell you a little bit about him. So first of all, he's going to be talking today about upcycling plastic into useful molecules. He holds one of the Mellichamp chairs in green chemistry at UCSB. And he's formerly a professor at Purdue and UCLA before joining UCSB in the last few years. Very eminent gentleman, has mentored more than 40 PhD students. He's the founder of a company called Spiro Renewables that is, taking the work you can hear about today and helping in the renewable substitutes for petrochemicals. He's a fellow of the American Association for Advancement of Science. He's got his PhD from Iowa State and a postdoc from Caltech. And with that, I'd like to introduce Mahdi, and we got a real treat in store. So Mahdi, welcome. Thank you. And I'll go on mute now.
Thank you, Mark, for the invitation and for the opportunity. Thank you, everyone, for joining us for today's seminar. If you would like to turn your camera on, that's fine with me. It gives me more faces to look at and maybe makes it easier for me to give this seminar. As Mark indicated, I wanted to tell you today about some of the research we've been doing with taking plastics, specifically polyolefins, and making interesting molecules from them. Obviously, plastics are everywhere, and there is no denying that plastics have improved our modern life. We use plastics in preserving food. We use plastics in our cars, which one could argue helps with energy savings, of course, in sports equipment, electronics, etc. So there's no question that plastics have made a big impact in modern life. And one could argue, what would we do without plastics, perhaps? But there's another side of plastics, which is how do we get from this wonderful thing of toys, saving energy in cars, to something that looks like this. This is Bangalore, the Arabian Sea. I figured I'm an Arab. I was born and raised in Jerusalem. So this is a fitting picture, although it's from India. And this is a gentleman, to give you the scale of things. This is this famous bridge in Bangalore. And you see, oh, actually, this is Mumbai. So I goofed. I said Bangalore, wrong. So the first mistake, if you guys want to keep track of all the mistakes I make, this is Mumbai, the Arabian Sea. And this is plastic garbage. So how do we get from wonderful things like this to this? And why do we have this double-edged sword? Part of the equation here is the growth in plastics, and this is, of course, adjusted to scale. But just to give you an idea, how much in 1950 we were making in metric tons or million metric tons of steel compared to million metric tons of plastic, and you see the growth going into more than 300 million metric tons annually of plastic that we are producing in 2018. And this growth is projected to continue to grow. And in fact, our own Roland Geyer here at UCSB has brought quite a bit of attention to this problem through many publications. One of them is this in Science Advances, where he basically projects at the growth of primary waste generated and how it will continue to grow into 2050. And the picture that Roland gives us is pretty depressing in a sense, because this is how much we will continue to discard, even if we revolutionized recycling. So we're now not recycling at all, which is a topic I will come to in a second. But Roland says, well, even if we really grow exponentially in recycling and we burn a lot of the plastic that we make, we're still going to be growing in how much waste we generate. And we have to do both of these things to get to plateau or level the curve. I guess this is a different kind of leveling than what we're used to with COVID, but similar idea. To get this leveling of the curve, we have to really continue to burn a lot of plastic. We need to continue to recycle at unprecedented levels that we do not have today. And I would argue, or one of the messages that I want to give you today is this is a really tall order, because even you and I put things in our recycling bin, it doesn't really get recycled. Now, when you talk about big numbers like this, tens of thousands of million metric tons of waste, etc., how can you visualize that? I mean, these numbers are just so big, it's very difficult to visualize that. Before we got into this area, I had a student in my group, TG, Talina, he's now a scientist at PNNL, that thought about this problem, and he computed the volume of the Empire State Building. And based on the density of polyethylene, he figured, or he calculated, that polyolefins alone, which is basically polyethylene and polypropylene for the most part, we make every year the equivalent of 300 Empire State Buildings built and filled completely with plastic. That's every year, and we repeat that, and that continues to grow roughly at few percent per year. So as I mentioned, polyethylene is king. So this is how much plastics we use and we make. Most of it is polyethylene. Then polypropylene is next. PET is third. Then everything else takes about 20% of what remains. So if we really want to make a big impact in recycling, particularly chemical recycling, which is what I'm going to tell you about, we have to tackle polyolefins. We have to tackle polyethylene and polypropylene. And in fact, PET is the one plastic that we do okay recycling. Again, mechanical recycling, you're always downcycling. So you're not taking a bottle back to a bottle, you're taking a bottle to something lower. Now, I mentioned that we don't really recycle, and I give credit to Roland Geyer for at least getting my attention to this problem, because I put things in my blue bin and I assume that they're being recycled. And this is a very powerful diagram where Roland shows us that only about 7% of all plastics are being recycled. So just because you see this sign on the plastic, and because you and I have blue bins outside our door that we put plastics in, does not really change the reality that the majority of the plastic ends up being discarded. And of course, some ends up into the environment discarded improperly, and that's a more complex subject matter probably. But at the end of the day, a very small percentage of plastics is really recycled. And you might say, well, wait a second. I mean, what's going on with recycling? And the hard message here, there's no better, there's no gentle way of saying it. Recycling is a lie that was created by the industry to sell more plastics. And in fact, as we went into the pandemic in March 2020, there was a great frontline piece on PBS that was titled Plastic Wars. And it basically educated us from people in the industry that the industry developed this whole recycling numbers that we see. PET is number 1, high density polyethylene is number 2, low density polyethylene is number 4, etc., before creating the appropriate technology to actually handle all that recycling on an economic scale that would make it viable. So there's also an article in the New York Times that's fantastic about this deception, if you will, of recycling. We put things in a recycling bin, but they don't really get recycled. And it's not because you and I, it's not because the consumer is not trying hard. It's because we don't really have a recycling technology that works today. And this is, if you allow me, I won't let it play for too long, but this is a piece from the front line, in their own words, so to speak, how this whole recycling scheme went down. Oh. I might have to share with you my sound. I apologize. I'm going to stop sharing. And I have to go back to advanced sharing. I forgot to click the right button. And now I'm going to go back to sharing my screen, and the sound should hopefully work. Do you guys hear it or no? No? Ah, bloody hell. All right. I don't know why we did that. I'm going to give it one more time. If it doesn't work, I'm going to give up on that.
It says you're sharing computer sound. There we go.
But even as Leesmer and his colleagues were publicly promoting recycling, privately, the industry had long expressed doubt it was ever going to happen on a broad scale. One internal document from the Society of the Plastics Industry cautioned, "The techniques of cleaning and separating the mixed plastics has not been developed for large-scale economic application." Another said, "There are no effective market mechanisms for mixed plastic." And this document was candid. There is serious doubt widespread plastic recycling can ever be made viable on an economic basis.
How could they go into all of these communities and tell
But
people
we can't see the
you
slide.
just have to recycle when they knew there were so many problems and so many hurdles?
Some were very skeptical, but felt they had to do it. I think others were more hopeful.
So it kills my sound when I share the slide. I apologize. I should have worked that glitch out before I got us going. So I'm just gonna, I just want you to hear that quote from I don't know why it's doing that to me. It's not letting me share both at the same time.
That recycling was ultimately going to work in a significant way.
Freeman's boss at the time, Larry Thomas, the head of the Society of the Plastics Industry, was blunt about it.
I was a front man for the plastics industry, no getting around it.
Thomas wouldn't sit down for an on-camera interview, but agreed to talk on the phone.
If the public thinks the recycling is working, then they're not going to be as concerned about the environment. I think they knew that the infrastructure wasn't there to really have recycling amount to a whole lot.
Thomas wrote.
So I'm going to go to sharing the slides. That's enough of the PBS clip. And I apologize that I did not have my act together to be able to do both sound and screen. But Any one of you that would like the link to that YouTube, I'm happy to share that link. I'm sure it's very easy. You could look it up, Plastic Wars by PBS, Frontline. And again, the message from the industry kept shifting. So there was the beginning, this whole setup of recycling in the 80s, and we need to do our job. And then in the 90s, the message shifted. And the rest of that piece that I was going to show you was really about the industry making a conscientious decision to put tens of millions of dollars every year into advertising rather than really trying to figure out an economic way of doing the recycling. So the message shifted in the 90s, plastics make it possible. And now we see into the 2000s and into today's time that the message, again, there is this alliance to end plastic waste that basically is telling us, you guys just are not recycling enough. You did not recycle enough, you need to keep recycling. And I just want to send a strong message here that when one of my students brought all this stuff to my attention, I did not believe it first. And I started doing all my research, and the conclusion was very obvious. The industry overreached by saying recycling is in place, you just need to recycle, you just need to sort, and that is absolutely not true. So in fact, to get to Rowland's curve and really increase recycling, we have to have significant technological advances that are going to revolutionize how we're able to recycle and the quantities of things that we can recycle. So there is a paper that I published with Susanna Scott and Sangwan Su from our place here at UCSB. And this was part of a graduate course that we taught together. And this paper in ACS Sustainable Chemistry and Engineering was actually Sangwan's idea. And it was a brilliant idea. He had the students in our class collect data on rates of degradation of plastics. And we unified all that data, and we developed this specific surface degradation rate that allowed us to compute in different environments how long it would take for plastics to degrade. So for example, a high density polyethylene bottle is pretty thin, and it would take about, on land, it would take about 58 years to degrade. But a pipe that's much thicker would take about 1,000 years to degrade. And to our surprise, we discovered that things like PLA, for example, will degrade on land about 20 times faster than high density polyethylene. And that's, I just picked a couple of different slides or pictures, figures from that paper. And I'm happy to say that that paper has been out for less than a year now, and it's been attracting a lot of attention because we sort of took data from the literature and put it in perspective that even if you have films that are very thin from polyethylene, they're still going to take many years to degrade. And they're going to be a little bit faster, perhaps, under photochemical conditions. But the interesting surprise was that land versus sea did not make very big differences. So when these things got into the oceans, for example, they were going to take very long time. If you have a plastic pipe in the ocean, it's still going to take 1,000 years to degrade, just like it would on land. And that's really part of the problem environmentally, is when these things get into the environment, because they are made out of carbon-carbon bonds and carbon-hydrogen bonds, they're very robust materials, they take a long time to degrade. And the degradation leads to products that are not always very desirable. And it all goes through nourish organic chemistry type degradation. It's oxidation, thermal or photochemical to give these type of molecules, compared to similar nourish type chemistry that will happen with PLA that essentially goes back to the lactic acid, to the monomer. So, and this is, again, I'm going to leave out of the equation something that a lot of people paying attention to, is that these plastics degrade and make microplastics that are entering the food chain in the oceans. The fish eat them, we eat the fish, etc. That's a whole different story I'm not going to even touch on. So what's the solution? I mean, I took a long time to get you excited about how important this problem is, how difficult this problem is. And I think the solution is not a one single pathway solution. We definitely need to continue thinking and developing novel plastics that are compatible with the environment, particularly for things that are going to be single use and going to generate large amounts of. But at the same time, we know that there are certain applications where the current plastics we have are going to be difficult to replace by biodegradable plastics. And I think this pathway here calls for developing new kind of chemistry, developing new kind of thinking. We're going to use these waste plastics as feedstock to do chemistry with them and make interesting molecules. One way maybe is to go all the way back to the monomer and not need to use virgin ethylene or propylene, but that's a high order. That's pretty difficult because of the energetics and how cheap ethylene and propylene are. So the story I want to share with you today is on this side, on the upcycling. And I want to start by saying, you know, polyethylene is an amazing molecule, but it's a very difficult molecule to do chemistry with because it's made out of inert carbon-carbon bonds and not very reactive carbon-hydrogen bonds. And I want to remind you that pyrolysis is always an option. And that's one of the things that Roland considered in his paper, is that we're going to incinerate a lot of plastics and we're going to just use it for low value energy and heat. But I take that as the low standard. We have to be able to do better than that if we're going to do interesting chemistry. I will take just a few moments to share with you some literature precedents for chemical upcycling. This is a paper from group in UC Irvine. They took polyethylene mixed with light alkanes, and they did sigma metathesis, or what we call in organometallic chemistry sigma metathesis. They use two catalysts. One catalyst does a dehydrogenation to install double bonds, and then they use an olefin metathesis catalyst. So they use a dehydrogenation catalyst like these iridium complexes, and then they use an olefin metathesis catalyst like this rhenium oxide or alumina to scramble the double bonds, and that results in breaking down the polymer to smaller pieces. The hydrogen that is produced from the dehydrogenation comes back to hydrogenate the double bonds, and you end up with smaller fragments, very long polyethylene to smaller fragments that could be used as hydrocarbon fuel, liquid fuel, jet fuel. That's a little bit better than just burning for the heat value. But again, this has multiple issues. You have to use an alkane as a co-feed. You have to use two catalysts, pretty complex. The productivity is not great. There was a paper that came right before our publication from colleagues at Argonne. They took single-use polyethylene, and in the presence of hydrogen, they used these platinum nanoparticles on STO, and they said we could break it down with hydrogen, do hydrogenolysis to these liquids that could be used as lubricants or jet fuels or things like that. That was a very interesting paper, but still it has sort of the downfall of requiring hydrogen as a co-reagent. This is the UCSB reaction. I've been taking the liberty to call this the UCSB reaction and to call the process the UCSB process. We did something that probably no chemist in his or her right mind would think of doing. We took this special nanoparticulate platinum that we make from cyclopentadiene platinum trimethyl. So we use a CVD method to make this very narrow distribution platinum on gamma alumina. And gamma alumina is slightly acidic, and that turns out to be important for this reaction. And we actually mix the polyethylene, and this is an SEM of our catalyst. We mix the polyethylene with our catalyst in a pressure reactor like this, and we let it go at 280 degrees. And then at the end of the reaction, so this is sort of like a solid-solid reaction, except we're going to a high enough temperature, of course, the polyethylene melts. So this is in the melt of the polyethylene. We don't get very high pressures because it's basically polyethylene. We don't add any hydrogen. We don't add any co-reagents. And at the end of the reaction, we open up the vessel and we actually get a liquid. The majority of our product is a liquid. We get some gases. We analyze the gases. I'll show you what these gases are. But we were pretty excited that the majority of our product is liquid. We get very little gases. And we do have some leftover, I'm going to call it char now, but we have some leftover solid. And it's not entirely char. Some of it is unreacted, recondensed type polyethylene. But that's besides the catalyst. So we separate the catalyst from this. We have a small amount of solid. The major products are liquid and small amount of gases. This reaction turned out to be much better than we thought, way much better than we thought, because if you run the reaction without platinum, just with gamma alumina, you get some product, but you don't get a lot of liquid product. And this is now different conditions with low molecular weight polyethylene. And in these instances, we analyzed the gas products. Well, we were very encouraged by this, so the students got excited and they went right away to actual plastic samples. I should have taken a picture of the plastic bag that we ran. It was not colored, by the way, so it wasn't this plastic bag. We shredded a plastic bag and we put it in the reactor with our catalyst, and that's low density polyethylene. And we took a milk jug and chopped up a small plastic piece, grinded it into small pieces, put it in the reactor, and we ran that. And that's high density polyethylene. And notice that these reactions actually work pretty well. High density polyethylene did not give us as much liquid product as the low density polyethylene. But I would say this is not a bad result. This is a really exciting result. So far, we don't really yet have a huge scientific insight. The gases were not anything unexpected. We make hydrogen, so we can detect hydrogen, and we make methane, ethane, propane, and those guys, basically, hydrogen is 2% of the 9%, and the low molecular weight C1 to C6 gases are 7%. What really got us excited is when we took the NMR of the liquid product. So I always like to say chemists worship at the altar of the NMR. My students know that every time they come to me with a result, I tell them, show me the NMR. That's the only way I believe any result. So when we looked at the NMR of the crude liquid product, we got really excited because the starting polyethylene had a CH2 to CH3 ratio of 20:1. The liquid product had a CH2 to CH3 ratio of 6:1. That's in the aliphatic region here. But what got us also really excited is we saw peaks out here, and we saw peaks in the aromatic region out here at 7 ppm. That really got us excited because we realized we are making aromatics. And when we quantified our aromatics, we're not making exclusively aromatics. Our mixture is about 60% aromatics, 40% chopped up, shorter length alkanes. So when we analyze this by GPC and other methods, I want to show you this is the starting polyethylene, low molecular weight polyethylene, Mn of about 4,000. Our product is around molecular weight 500, and this is the refractive index detector. And we did a UV detector, and you see that they superimpose. That gives us very strong confidence in we're making aromatics. Again, the proton NMR, the carbon-13 NMR were very indicative of making aromatics. And then we did FDMS, which showed us that we're making cyclic alkanes as well as alkylbenzenes. Now, this is exciting because these long chain alkylbenzenes are actually called lab linear alkylbenzenes. And when the benzene is sulfonated, these make detergents. All the detergents that we use are actually sulfonated lab alkylbenzenes that are sulfonated. That's brilliant because we could take the aromatics, sulfonate them, and that would allow us to have an easy separation from the remaining hydrocarbons that can be used for something else. And these can be used in detergents. And as a matter of fact, the sulfonated alkylbenzenes are reasonably degradable. So the story has become now very exciting, except we were missing a scientific piece. And the scientific piece that we were missing is that my chemical engineering colleagues kept yelling at my collaborator, Susanna Scott, and I, saying, "You violated thermodynamics. How could you make alkyl aromatics at 280 degrees C? Something is wrong with what you're doing." But I want the crowd to remember that I'm a chemist and I worship at the altar of the NMR. So the NMR could not have lied that we've made alkyl aromatics. We just needed to understand how are we not violating thermodynamics, because we cannot violate thermodynamics. So this is how the chemical industry makes these alkylbenzenes today. They take naphtha, interestingly, with a platinum catalyst on alumina. It's a rhenium platinum catalyst, usually 500 to 600 degrees, to make these BTX, benzene, toluene, xylene. And then they use long chain olefins with acid catalyst to alkylate the benzene or the toluene to make these dialkyl aromatics. We are making this in one step at lower temperature with one catalyst, no solvent, no added hydrogen. So how are we getting away with this? It required a bit of thinking, and it required a bit of computations that were done by Baron Peters, our former colleague in Chemie, that he left us to Champaign-Urbana, unfortunately. It turns out that we're making cyclic compounds that then can aromatize, and that's definitely uphill, but we're paying the price for this by using the hydrogen that is produced to chop up our chains. In other words, we were driving this reaction towards aromatics thermodynamically by taking the hydrogen and using it to do hydrogenolysis and cut our polymer chains into smaller chains. So these processes that we're doing hydrogenolysis were what was allowing our thermodynamics to work out and allowing us to get the aromatic products that we were getting. At this point, under my colleague's leadership, under Susanna Scott's leadership, she said, we need to submit this paper to Science because we have something interesting and we have an explanation. We are not violating thermodynamics. We have an explanation as to how we are getting to the products. And when we collected kinetics on this reaction, actually our predictions and our modeling came out to be much better than we thought. So this is in real time making liquid products, and we analyze the dispersity of our product. So notice we end up at the end with a very narrow dispersity of these alkyl aromatics that we made. And this is our average carbon number, or our MN, as we go to smaller chains. And in the blue solid line, the dots are experimental data. The blue solid line is actually the modeling that Barron and his student did based on the mechanism that I just showed you in the slide before. And the agreement is just amazing, is phenomenal. And now the gray area is basically the statistical error in our model. And you see that our experimental data fits very well. So we're not violating thermodynamics. We are actually able to get to these products because we use the hydrogen that we produce from the aromatization to chop up the long chains of our pollen. So we published the paper in Science. I don't know, I think I put the reference. We published the paper in Science, and wow. My speaker died, or do you guys hear me?
Yes.
Oh, sorry. My Bluetooth device gave out on me, but I guess the computer went to the default, so we're all good.
Yeah, we can still hear you, Mahdi.
All right, sounds great. So we published the paper in Science, and the editor at Science solicited Bert from the Netherlands to write a little highlight about the paper. And I'm happy to say, in this perspective that Bert wrote, he actually came up with a much fancier figure than the figure that we came up with at UCSB for our process. So I like to use Bert's figure here. This is the UCSB process. Bert from the Netherlands came up with a much better and much fancier figure than I could come up with. Of course, recycling the catalyst is very important, and this took us some time to get to the right conditions. Unfortunately, our recycling is not perfect. We can recycle the catalyst. It gives us lower activity. The distribution of products between aromatics and linear alkanes is still the same. But what was encouraging is we lost activity on the first recycle, but as we did more recycling, we seemed to plateau in that lower activity, which at least for us as catalysis scientists was good news. Of course, more work needs to be done on understanding what the catalyst is doing in the degradation, how we can improve the recycling and the activity. And there is no question the data I showed you shows that our reaction takes about 12 hours to get to a reasonable conversion. And we definitely have to speed the time scale as well. But you know, sometimes I pretend that I'm an engineer, so I took the liberty of putting a process together. So I modeled this on putting a kilogram in of plastics, and I made some assumptions about what it's going to cost us per ton of plastic to put the plastic in here. And I wanted to figure out, I made some assumptions on how we separate the liquids. What we do with the solids, we basically dispose of them or use them as a heat source. And I just wanted to draw your attention to, even if we were paying for this plastic $5 per ton or even $10 per ton, we are generating products here. The alkyl aromatics alone are around $1,000 per ton. So just on a first techno-economic pass on the process, with all the costs in the operational units being put in here on a very primitive level, shows you something that's very exciting and very encouraging. One of the areas we know we have to improve is definitely the the catalyst usage, because we are using a significant amount of platinum under the condition that we're running under now. And that's an area that we look forward to improving, because it'll make this UCSB process even more appealing and more exciting. So I want to wrap up here by saying, I hope that I convinced you today to think in a new way. What we've been doing is find a hole in the ground, get the resources out, make, use, throw away. Once we throw away, this is going into a landfill, going into incineration, going into the environment. We got to stop thinking linear. We have to start thinking about this after the use as a feedstock. Even if we're not closing the loop completely, at least that end plastic waste is a feedstock that we need to use for making chemicals, making new materials, etc. And I think people in the materials world, this is a very cool recent article in Macro Letters, in ACS Macro Letters. Even people from the materials side are starting to really understand the importance for making materials that meet the performance, but are designed for this circularity. Remember, all this polyethylene, polypropylene, when we made it as chemists, we were not thinking about circularity. We did not really think about putting that aspect in the design. In fact, some of the things that we're working on in my laboratory now is thinking about how to make the same polyethylene material that we make today that has the same properties, but it has in it, if you will, it's a Trojan horse idea, has in it, for example, something that's going to be targeted by a specific catalyst to allow you for that circularity, to allow you for that new type of thinking. I want to end here by saying, you know, we spent many decades mining below the ground. I want to sell the crowd on mining above the ground, even though this is not me, but I like to think that, you know, this is an idea now to start thinking about all this plastic waste that we are producing on annual basis is a feedstock, is a chemical feedstock that we should start using instead of keep pulling things from a hole in the ground. I have to say, I did none of the work that I told you about. This is a very important message. I'm just blessed to work with very smart people that allow me to be a cheerleader and give me the permission to talk about their beautiful science. This has been a fantastic collaboration between myself, Susanna Scott, Baron Peters, and Anne Lapointe from Cornell. Danny and Ariel are my students. Fan was a postdoc in Susanna's lab, and Jakai is in Susanna's lab. But truly, I think of this work as a teamwork. Ryan has done a lot of the computations, and he's in Baron's lab. This has been a blast working with really, really smart people here, particularly, not to take away from this side of the slide, but particularly working with this is where the credit goes to the hard work of these very smart young individuals. And I'm just blessed to have the opportunity to work with smart people. I want to acknowledge, actually, we got started with all of this probably 3 years ago with a very small grant from the CNSI, and we used some money from the Mellichamp Academic Initiative, and now we have funding from DOE for this upcycling of polyolefins. This brings me to the end. I'm happy to answer any of your questions, and thank you so much for your attention.
Well, thank you, Mahdi. That was great. So let's open up for questions. Please unmute. Feel free to unmute yourselves and jump in. There's a question that's come up. Hannah, if you want to unmute yourself and just ask your question, that would be fine. And if not, I'll
Sure.
go ahead.
I was just wondering why, if there was a specific reason why the solid char byproduct could not be downcycled in a similar way to the incinerated plastics, or if that's not the most efficient way to use them.
It can. That's actually the low-hanging fruit for that. And that's the assumption I made in this techno-economic analysis. I used this solid organic byproduct for its heat value. It can.
Thank you.
So, other questions? I mean, Mahdi, it's interesting because I'm not a chemist, I'm a computer scientist. And so I have all these questions, but the chemists and chemical engineers who are on this call are, they'd be simple questions. But I guess, let me ask you a layman question. One of my wife and I might ask you, from a non-chemist perspective. So if you could wave a magic wand right now and sort of change a few things about this whole process, just make sure I understand, or what you would tell the, if ABC News or somebody calls you, what are those things that just a couple magical things you could do in the sort of the overall process, of the way we produce plastics, the way we, recycle and so forth, that you could just wave your wand and change so for the lay person.
So in terms of our UCSB process, or in terms of the big picture of how we use plastics?
However you want to answer the question, whatever you're.
That's a really hard question. So for our UCSB process, I would really say one of the things that we've been focusing on is, now that we understand we make the aromatics by using the hydrogen into chopping up the polymer into smaller pieces, we're really looking, at least theory tells us, we should be able to get to 70–80% aromatic selectivity. So we should be able to do better than the 50–60% that we've been seeing. And the second piece is, I would want to do this with a catalyst that can be robust. I can use 10 times or more less catalyst, and I can recycle it a lot, basically. And I think that's going to make, an amazing process. And the last one is, which we're already starting to do, can you do plastic mixtures? Notice I showed you a milk bottle, I showed you a plastic bag, but that is still not a very sophisticated polymer that's a mixture of different materials. And if we're able to target mixtures, because even packaging that we use for food has in it complicated things on the surface to prevent gas penetration, etc. On the big plastic picture, if I were to wave a magic wand, I would make materials that are very competitive in price and performance to polyethylene and polypropylene that degrade as well as PLA, or even better, particularly for single use.
So when some stores have, like, they claim their cornstarch bags and things like other kind of materials, are any of the things that are currently out there actually sort of working, or is that again part of the marketing arm of the industry?
I think it depends on who you talk to, right? Life cycle analysis is important for some of these things. My understanding is we really don't have things that can compete in terms of performance to polyethylene and polypropylene. Although I'm a big advocate of PLA, there's a lot of things, in that we could use forks, knives that are PLA. They are degradable. The problem is that, because of this whole recycling thing, the PLA plastic, you're not supposed to throw it in the recycling bin. But I notice even on our UCSB campus, a lot of students and a lot of adults, they throw their PLA stuff into the recycling bins. So there is everything humans do becomes very complicated, right? That's a human endeavor.
I have a question about whether you think the molecular processes, the reaction mechanisms that are occurring place, are they primarily intra-chain, or do you have a lot of inter-chain processes going on? So does one chain start to, form 6-membered rings and then aromatize along its backbone, or do you have massive inter-chain interactions here?
Excellent question. I love that question. The honest answer is we don't know yet. The hypothesis we have, or the working hypothesis, is we get cyclization within the same chain, and we get hydrogenolysis, of course, with different chains, because that's the hydrogen product that comes. We also get hydrogenolysis from cyclized chains, because they would start with very long chains on the 6-membered ring. How much we get crossing between the chains has been a difficult one to answer, and part of it is we've tried to trap olefins or double bonds. Do we make vinylidene or vinylene in the chains? And that would allow for basically cross-linking or interchange between chains. And we have not been able to detect any vinylenes during the course of our reaction.
Mm-hmm. In general, I really like your approach. It'll be interesting to see as you start to look at other plastics, if they hurt your catalyst, if they, coordinate and mess up your catalyst with, but even if you could just deal with all the polyethylenes, it'd be awesome.
Right. That's a really excellent point, because we know for sure, I can tell you for sure, that we cannot use our catalyst with things like PVC, because any halogens basically poison our catalyst.
Sure.
But to your question, is a small amount of things like EVHO on the polyethylene, small amount of heteroatom oxygen, is that gonna affect our catalysis? We're looking into that, actually. We've been doing experiments down those lines.
Yeah, it was a very nice talk. I really enjoyed it.
Thanks.
Louis, those are great questions. Louis, appreciate you joining us today. Louis has a significant background in this space, as you probably know, Mahdi. So other questions for Mahdi? We still have a few minutes left if somebody has something interesting they want to discuss. Okay, all right. Listen, this was just great, and we really appreciate Mahdi, you doing this for the IE seminar, and we look forward to working with you more carefully. And I hope, from those who are in the audience today, especially if you're not just, whether you're at UCSB or you're in the community or even beyond, I'm sure Mahdi would be happy to, entail follow-up kind of discussions or questions.
Absolutely. It would be my delight. Reach out, and I'm happy to answer right away.
So, and again, coming up in a couple of weeks, Josh Smith in Perpetual Computing, Eric Mazanet in March, Yufei Ding in sort of on the computing side of things in April, and we'll have a quantum talk from Galen Moody in May, and there'll be some other talks sprinkled in as those come online. So thank you very much.
Thank you
for Energy Efficiency appreciates it. Thank you so much, Mahdi. Thank you everybody for joining us, and we'll see you in a few weeks.
Bye-bye.